consists of matrices of this form A minus B conjugate, B A conjugate with A and B in C. And we can consider H as R vector space, R1 plus Ri plus Rj plus Rk in M2C, where 1 is the identity matrix, and I, J, K, we already seen them yesterday in the Lie algebra SU2. And as multiplication is the multiplication of matrices, and the center of the quaternion algebra is R1. And we define H star as the conjugate transpose of X in H. And we define the function n as x star x equal to x star, and it will be the determinant of matrix X, and it will be in R1. And then the trace as x plus x star. And we also define an the inner product as you see there, and we can identify all the x in H where the nx is 1 is become the SU2, and it is in the set of unit of H. And SU2, the Lie algebra, is generated by I, J, and K, and so the H without R1 will be this Lie algebra SU2. And now we consider this map Lxy and Rxy. And we will see that this map are orthogonal if and only if the nx is 1 and also the determinant is nx squared. And orthogonal means here preserve the inner product. First, we compute for y and z in H. By definition, Lxy is xy and Lxz is xz, and the definition of the inner product is this xy star xz plus xz star xy, and you can get that this will be x star x times the inner product of yz. So it's easy to see that if Lx is orthogonal, means preserve the inner product, so this x star x should be 1, and it means the nx equal 1. And in contrary, if nx equal 1, so this is 1, and then this is preserved. In the same way, we also have for Rx. And for the determinant of Lx is equal to determinant of Rx and equal to nx squared. If we compute the character polynomial of Lx when x is in R. So, sorry, it's rather confusing. We will use the same letter x. Oh, I write it like this. So the character polynomial of Lx will be for x equal for x in R. This will be x minus x power 4 because this is 2 by 2 matrix. And when x is not in R and this x star is not equal to x, so we can have the minimal polynomial of x over R is this px x minus x times x minus x star, and this is x square minus trx times x plus nx. And we can compute that this is x plus x star square minus 4x x star, and this x minus x star square, but this will be a negative number because this is imaginary. So this is smaller than 0. So fpx has no real roots. So it means that we will have the characteristic polynomial will be the power of this px. This will be px square, and in particular the determinant of Lx will be equal to determinant of Rx, and this will be nx squared. For the detail of this, you can do it in the training session tomorrow. So anyway, what I want to mention is when the characteristic polynomial is this px squared, it means that the determinant will be this nx squared. And now we go back to we define a new function cx. Cx, first we take x in the set of the unit of age. So maybe I write it like this. And define Cx from y to x, y, x inverse. And this function is invertible and on R1 it is the identity. And if we restrict to V, V is the subalgebra of H generated by IJK. We restrict this Cx will go from V to V. It means we can get a function C that goes from the set of the unit of H to GLV. And this is a group homomorphism, and this sends X to Cx. And now when X is in SU2, and because Cx is the composition of Rx inverse and Lx, and we have seen that these two maps are orthogonal. It means that Cx also orthogonal and has determinant 1 by that formula. So we can moreover restrict this C. Now it is from SU2. And this will go to SOV, and SOV is isomorphic to SOR3 because we can identify V with R3. We can have that the image of this restriction will go to SOV because, as I said earlier, we have the determinant of Cx is 1. So now this X goes to Cx, and Cx sending Y to X, Y, X inverse. And it's easy to see that when you have this as identity, so the X should be 1 or minus 1. So the kernel of this homomorphism from SU2 to SOV is the matrix 1 and minus 1. And now we will show that the image of C is SOV. And by showing that the image is SOV, then we will get later on the isomorphism SU2 modulo -1, 1 is isomorphic to SOV or SOR3. Or we usually also call it SO3. Okay. And now we start with the, I will not go too much in detail on this. I will just give the generators of this SO3, and then taking the generator of this, we try to find X such that this X will go to that generator. So the generator of is given by these three matrices. And if you recall that SO3 is the group of rotation, and the second one is and the third one is and we take all for all alpha, beta, and gamma. So if we can find an X that will be sent to this, and then another X that can be sent to this one, and one more X, another X goes here, then we can say that this map is surjective. Okay? And this is quite a long computation. Let me call this matrix, this is A, this is B, and this is C. And let me take for A, maybe I call it XA, is this matrix. And then this XA sorry, yes, X, Y, X inverse. From this XA, we have CXA, but CXA is from V to V, and V was generated by I, J, K. So once again, I will use the generator. I will not compute all. So let us see what here for I. This will go to XA times I times XA inverse. For J, this will go to XA J XA inverse, and K, this will go to XA K XA inverse. Okay, I will just give the result. So XA I XA inverse is sin alpha I plus cos alpha J. So after multiplying these three matrices, you will get this, and for this one cos alpha, and then minus sin alpha, and for XA J XA inverse, you get sin alpha I plus cos alpha J. And how do we get this matrix? So we write down this matrix for A. But we write it down on row. Okay? So the first row, this cos alpha minus sin alpha, and then no K. So this, what do you call it? CXA is this matrix, cos alpha minus sin alpha, and then 0. So usually we write it on column, but here we write it on row as the linear combination of I, J, K. Here cos alpha minus sin alpha and 0, and then sin alpha, cos alpha, 0, and for K you can guess that I didn't write it down here, but this XA K XA inverse is K. So this gives us 0, 0, 1. And this is for A. For B, the XB is this cos beta over 2 minus and for C is this. And then you can play by computing all of these matrices, and you will get the matrix representation of this homomorphism will be B and C. So we conclude that for the generators, it has a pre-image, and we conclude that this homomorphism C is surjective, so we have this isomorphism. So the confusing part is to show this isomorphism, but then after we get this isomorphism, to get the representation of SO3 is easy, because now we can try to find the irreducible representation of SO3 as the irreducible representation of SU2, on which the subgroup 1 and -1 acts trivially. I will explain it now. So yesterday we have defined phi from SU2 to the endomorphism of CXYD. And this was defined as phi u of fz goes to f of u prime z. Now, if you take u, so the kernel was 1 and -1, means the identity and minus identity. When you take u equal -1, you compute this fu fz, you get f of minus x minus y, and this will be AD x power, minus x power d plus AD minus 1 minus x power d minus 1 y, and the last one is A0 should be -1 minus y power d. But then in SO3, let me write it phi hat. Phi hat of u is identity. So this phi hat of u on fz should be fz. So it means that the f of this one should be equal to f of xy, and this will happen when d is even. So therefore, for the irreducible representation of SO3 are those endomorphism of the representation is 1 and 2 and 3. 1 and 2 and 3 part of CXYD, only the D is even. So representation of SO3 is CXYD, or if you want, you can write it like this, 2K, or no, I don't know what letter we haven't used. Okay, just write it like this, and D is even. Oh, okay. In here it is written like this. For the irreducibles, are the VI's where it's called CXY2I. Okay. Now we will discuss about the Peter-Weil theorem. And first, I will remind you what is an inner product. An inner product space is a C-vector space with an inner product that is positive, Hermitian, and sesquilinear. Sorry. This should not be number 4, okay? Should be only 3. And an inner product space V is called a Hilbert space if it is complete for the norm induced by the inner product. Complete means every Cauchy sequence is converged. And now let G be a compactly group contained in some GLNC. And we define L2G as the completion of the vector space CG. I think in the previous lecture we have seen something like this. So CG is the set of the function, square integrable continuous function from G to C. And on CG, we define the inner product of f and g as the integral of f g bar mu. And mu is, you can think of like a volume, and left invariant volume means it's invariant under the left multiplication that we defined earlier. And this CG is, so L2G is the completion of CG. We will see an example of mu later. But for the theorem says that, okay, before the theorem, we define a so-called Hilbert basis as a complete orthonormal subset of a Hilbert space. And here complete means that the S-perp is 0. And we can have CG as a representation of G. this sends G to rho G, where rho G send F to G times F, and G times F, okay, so G is not a function, it's an element of group. Usually when you see F and G, you think of they're both functions, but not here. G is in G, but F in CG, and G times F is defined as this function that's sending X to F of XG, and GF in CG. And this action is linear and preserve the inner product and can be extended to an automorphism of L2G. In this theorem, we will give an isomorphism between L2G and the completion of the direct sum of endomorphism of Vi, where Vi is a set of representative of the isomorphism classes of irreducible finite dimensional representation of G. So we will show that by showing that given this square root dimension Vi times this function Fijk form an orthonormal basis of L2G. So we will show this isomorphism by showing that these give orthonormal basis of L2G. Okay. So first, each endomorphism is a representation when you define G times M will be this times M, and also for L2G we can also define like here that the GFX if Fxg. So this side is a representation of G via this, and for L2G is also a representation via this equation. So now we define psi from the endomorphism of B to L2G, sending M to psi M, and where psi M of G Remember, L2G is the completion of CG, and CG is a set of functions from G to C. So you have to give psi m of G is defined as the trace of this matrix times M. So Vi is the representation of this one. And also for G in G and M in endomorphism of Vi and X in G, the psi of Gm, so we have defined psi from M to psi M given like this. And now if we have G in G, psi of Gm, put it on X, where X in G, by definition is the trace of phi I X times Gm, but Gm is phi I Gm here. And because phi is homomorphism, you have this, and this is phi m of xg, and this is equal to g of psi m x. Because the definition was like this, like you're from here, like this psi m in L, and then g f x, g psi m x. So it means that psi is a morphism of representation and if we put the direct sum of this, and we will get that this is also a morphism of representation. And now, in order to show that it is isomorphism, we will show that it is injective and surjective. For the injectivity, we will show that square root of dimension of Vi Fij will be the orthonormal basis of L2G. And so first, let us compute so the idea is now we want to compute this, so we want that the square root dim Vi Fi J K orthonormal basis. So when you have and then you multiply with I don't know, what do you want to call it now? So there Fijk and then dim I beta gamma. And we want this equal, so this will be equal to dim Vi. And so we want this to be 1 if J equal to beta and K equal to gamma. And if we will see that when this is Vi and the other is Vj, then there is no, so the inner product will be 0. But in order to compute this, so this is defined as the integral Fijk Fi beta gamma bar mu, and okay, I should put G here. And the Fijk is given here as this inner product. Rho ij phi ik phi ij and rho ij phi I gamma first, yes, gamma phi I beta bar. And to make it simple, let us now compute, let's take G equal G, U and U prime in U and V in V, and U prime and V prime in V prime. Let us see this first. We will compute I change this with GU and this with V, and this with GU prime, and this with V prime. We will show that this is 0 if V and V prime are not isomorphism, and this is equal to UU prime VV prime bar over dimension V. If V and V prime, equal V prime. So, like I said before, so there is no use to compute between the different VI. We just need to compute here where the I is the same. And what else? And to make it simpler, the computation of this, we change it to GUV and GU prime V prime. And now we will compute this. First, we will need let F from V to V prime a linear map. And we can define this big F as this integral. And we can show that this is a morphism of representation. We check this will give us G, F, G prime HX. And since we have this, it's like the sum of all over G, so we can replace this G with HG. So also here, this is the same as HG F HG inverse HX mu. And this is equal to and this is equal to HFX. And if V and V prime are not isomorphism, then we will get that F is 0. And let us see here. So if we define F from X to and since V and V prime are not isomorphous, so we will have this and by definition the FV is this integral. And because this is a morphism of representation, you can multiply with G inverse and you get this. And when you change F with this, you can take this out. And multiply again with G. So we get that if V is not isomorphic to V prime, then this integral will be 0. And now if V equal to V prime, then F will be lambda I, where lambda is like the eigenvalue. So we can compute this. This is the trace of F. And this is also the sum from I from 1 to dimension of V. And this is the integral and this is also, when you add this, you get the trace of G, F, G inverse. And because we go for all of G and G, this is equal to the trace of F and this is equal to trace F, and F is Vi U prime Vi, and this is and finally, this will be the same as U prime times U. Yes? Okay, so where was I? So anyway, so this, where were we? Okay, so what I want to say is now, that, okay, I kind of lost in here. We all do. So, okay, so now, so we'll get that integral of GUV so it means that when this is 1, so this one will also be 1, and this Fijk will be orthonormal basis, and that gives the injectivity. And if I have time tomorrow, I will explain for the surjectivity. Thank you very much.